Hello, this is the second mini lecture, and as a reminder, this lecture series is intended to introduce new students to the fundamentals of solid-state physics, and today we'll be discussing the reciprocal lattice. So the reciprocal lattice is a concept that you might not have real-world intuition for at this point. However, it does touch on concepts that you have seen in some earlier coursework, probably. So one aspect of the reciprocal lattice is that it is the Fourier transform of the direct lattice. So I'll do a quick little proof of this after I introduce what the reciprocal lattice is, but I want to remind you that the definition of a crystal is a material that has some regularly repeating structure in space. So it has a unit cell composed of some arrangement of atoms that is repeated over and over and over again. So if you have a structure that is repeating, that has some periodicity, the natural mathematical technique to simplify that information, to display that information in a more compact way, is a Fourier transform. So just as an example of this, if you have a function that's a sine wave in the time domain, the essential information is captured just by the frequency rather than the full sinusoidal wave going on forever. So that's one way to think about the reciprocal lattice. And another way to think about what is going to be discussed in this mini lecture is it's going to be sort of a more formal version of Bragg's law. So as a reminder, Bragg's law is something that you might have seen in a freshman physics course, and it is this equation. So if you have some periodic structure, like perhaps you had a demo in your class of a diffraction grating, then when you shine light of wavelength lambda on it, that light will get diffracted in such a way that follows this equation. So n here is an integer. Lambda is the wavelength of light. D is the spacing of the periodic structure that's diffracting the light. And theta is the deflection angle of the light, the diffraction angle rather. So as a reminder of this concept, let me just do a very quick demo. So this is a diffraction grating. You might have done a demo like this in your earlier classes. And if we want to know what D is for this object, we just look at what it says. And it says 1,000 lines per, whoops, it's flipped. It says 1,000 lines per millimeter. So D is a micron. For this diffraction grating. And typically, D will need to be comparable to lambda to achieve diffraction. The wavelength of visible light is on the order of 300 to 700 nanometers. So this is comparable to a micron. All right, so let's see if we can get this to work on my screen back there. So I'm going to shine a green laser pointer. So here's the green laser pointer by itself. And then I'm going to shine it through the diffraction grating. And you can see now, oops, my background's not making this easy, but I hope you can see that now, in addition to the central transmission spot, there are two other spots, which are the diffraction spots. And you can basically connect this to the angle theta by knowing the distance between the grating and the screen that the dots are being displayed on. And you can see that when I move the diffraction grating closer to me and further away from the screen, then the dots move further apart. Okay, so this is diffraction for visible light. If you want to do the same exercise with the periodic structure of a solid state system, where the space, the D is set by pretty much the atomic spacing, you're going to need X-rays or neutrons or electrons. And I'll get to that a little bit later. But now let me start by defining what the reciprocal lattice is. All right, so as a reminder, the direct lattice is represented by primitive translation vectors, which are called A1, A2, and A3. And this, again, is the direct lattice. So that's the regular real space lattice from the first mini lecture. So now the reciprocal lattice vectors, they are going to be called B1, B2, and B3. And they are defined as follows. So I'll write down the definition for all of them, but it's going to be a little bit redundant. So B1 is defined as 2 pi times A2 cross A3 divided by A1 dot A2 cross A3. So all of these should have vectors. So that's B1. B2 is going to be equal to 2 pi times A3 cross A1 divided by A1 dot A2 cross A3. And finally, B3 is going to be defined as 2 pi times A1 cross A2. And then the denominator is same as before, A1 dotted with A2 cross A3. Okay, so these are the definitions. We will, let me now add a little bit of intuition about them. So first of all, the denominator of all of them is a scalar, and this scalar is the volume of the primitive cell. So this is okay. So the reciprocal lattice is very simple to calculate. You don't even need to calculate it if you're in some sort of crystal system where all of the primitive translation vectors are perpendicular to each other. So, for example, if you have a cubic system, a tetragonal system, an orthorhombic system, in those cases, you don't really need to calculate anything. So if A1 is perpendicular to A2 and perpendicular to A3, then your reciprocal lattice vectors are going to be very simple. So B1 is going to be equal to 2 pi, whoops, let me, 2 pi divided by the magnitude of A1 in the direction of A1. So I'll just write it as A1 hat, and then I'm not going to write down the rest of them because the same statement, just switching out the subscript, is going to be true for B1 or B2 rather and B3. So this statement is only true if all of the direct lattice vectors are mutually perpendicular. If they're not all mutually perpendicular, then you have to go ahead and do the cross products. Let's see. So what other, okay, so something that is always going to be true is that the reciprocal lattice vector with some index I dotted with the direct lattice vector with the same, whoops, this is supposed to be I, with the same index, well, let me actually write it as a j. So bi dotted with aj is equal to 2 pi delta ij, which means that it's equal to 0 if the indices are different, and it's equal to 2 pi if the indices are the same. So basically, b1 dotted with a1 is going to be 2 pi, b1 dotted with a2 is going to be 0, and so on and so forth. And this is something that you can use to double check um, whether you calculated your reciprocal lattice vectors correctly. So let me just define what this delta is. So delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. Okay, so that is the definition of the reciprocal lattice. And let me put a box around it. And the rest of the lecture is going to be essentially sort of connecting this to experiments for learning about the structure of materials and also gaining some more intuition about what the reciprocal lattice actually is. So a concept that that we're going to be using, or some notation that we're going to be using, is that we can construct all of the reciprocal lattice, all of the reciprocal lattice vectors in the following way. So any reciprocal lattice vector can be written as v1 times b1 plus v2 times b2 plus v3. Sorry, let me make the v's look the same. v3 times b3, where v1, v2, and v3 are all integers. So any reciprocal lattice point, any generic reciprocal lattice point, will be using the notation G to describe it. Just as a reminder, if we're talking about the direct lattice, usually the notation is T, and any point in the direct lattice can be written as U1 times A1 plus U2 times A2 that's supposed to be, plus U3 times A3, where AU1, U2, and U3 are also integers. So just to make this point a little bit more explicit, if we have some sort of direct lattice, let's make it very simple. Let's make it a square lattice, and a lattice is an infinite object, so this would go until infinity, but I don't have time to draw infinite points. So let's just draw these points. So if we have uh, uh, the spacing as A, this is the direct lattice, and it's a collection of points in space. The reciprocal lattice is also going to be a collection of points. It's going to be a collection of points in reciprocal space. So this picture is not going to be to scale relative to the previous picture, but I just want to emphasize that the reciprocal lattice, just like the direct lattice, is a collection of points in space. So this is the reciprocal lattice, and it's not the direct lattice because of units. So these units are going to be in units of inverse length. So the spacing between adjacent points in this sort of square lattice is going to be 2 pi over A. Okay, so um, so if you haven't studied solid state physics before, the reciprocal lattice might be something that is new to you. And students often wonder whether the reciprocal lattice is like a real object or a conceptual object. And and a reciprocal lattice is not really something that you necessarily encounter too much in everyday life, but many experiments that, if you continue doing research in solid state physics, I do every day, many experiments for measuring the structure of materials indeed measure the reciprocal lattice, not the direct lattice. And this is sort of an analogy to like if you're listening to music, for every note, you sort of hear a pitch, you hear a frequency, you hear the Fourier transform of the time domain information. So similarly, many experiments for measuring structure sort of give you information straight out of the measurement instrument about the reciprocal lattice, where if you want to then gain information about what is happening in real space, you have to do a little bit of processing or interpretation to get there. So let me illustrate this point with some data. The reference for this data is linked below the image. And this is neutron scattering data. So neutrons are neutral particles, and it turns out that they can be prepared such that their de Broglie wavelength is comparable to the atomic spacing in a material. So those neutrons can be used to learn about structure, among other things. So let me give a little bit of context here. So a lot of neutron scattering data, they use this HKL notation, where essentially H, K, and L represent different directions in reciprocal space, the X, Y, Z direction in reciprocal space, respectively. So these data here are taken in the HK0 plane. So essentially they're setting the last unit equal to 0 and just taking a slice in that plane. So the x-axis is sort of the x-axis in reciprocal space, the y-axis in reciprocal space. And you'll notice that there is a regular arrangement of bright yellow dots. So in this color scale, the yellows and also the blues, but more the yellows are where there's the highest intensity neutrons that are diffracted. So these brightest dots, if you look carefully where they're located at all of the integer locations. They're located at h equals 2, 3, 4, 5, 6. L equals 1, 0, 1, 2, 3, so on and so forth. So they make an integer grid, and each of these bright yellow points essentially represents the points on the reciprocal lattice. So each of these points can be described as some reciprocal lattice vector and using the equation that I had on the previous slide. Okay, so basically, just to summarize everything I just said, the bright yellow dots here represent the reciprocal lattice. So if this material that was being studied in this paper was a perfect crystal, then the data that they would get would just essentially be bright yellow dots with maybe some broadening due to temperature, maybe not. Well, 6 Kelvin isn't very high, so maybe not. And then some broadening due to the instrument's energy resolution. However, there is some more structure they see, like there are these diagonal streaks that you can see in light blue. And basically, this additional structure on top of these bright reciprocal lattice points indicates that something else is going on, and that something else is what is explored in this paper. So this picture is just intended to be an example of how the reciprocal lattice can be a real object in the sense that it is something that is directly measured by experiments. So the data here are probably pretty close to how they come out of the spectrometer. Whereas if you want to translate this information into real space, if you want to make a picture of what the crystal looks like with the unit cell repeating over and over, you can do that, but that's an extra step. Okay, So, all right, so I've introduced the reciprocal lattice, and at this point, I want to touch back on the points that I started with. And also I want to try to give a little bit of intuition about the reciprocal lattice. So I mentioned that the reciprocal lattice represents the Fourier transform of the direct lattice. And let me show this here. So Fourier transform, I'll abbreviate that FT. So I'm going to write down the derivation only in one dimension, but in the notes that are also posted, I'll have the same thing um, uh, um, from a higher dimension. Okay. All right, so let me show that. So I'm going to draw a one-dimensional uh, lattice, and this is intended to be a direct lattice. So this is the x direction, and the spacing between any 2 points is a. Um, so in general, if you see a drawing like this without any context, if the units are a, you know it's a direct lattice. If it's 2 pi over a, you know it's a reciprocal lattice. Okay, so we can write sort of this structure as some function of x. So I'm going to call it L of x, and we're going to write it as a sum over all integers, which I'll label u1, um, and uh, and at every lattice position, we're going to have a delta function. So x minus u1a. Okay, so u1 is an integer. And basically what this equation says is that it just describes our lattice as a line of delta functions separated by spacing a. So we can write the Fourier transform of this object, and we're going to write it in a standard way. So the Fourier transform R of Q is equal to an integral from minus infinity to infinity e to the I q x times L of x, and then integrated over dx. And plugging in what we have for our original function, L of x, we have a sum over u1. Then we have an integral from minus infinity to infinity e to the I q, whoops, qx, then delta x minus u1a integrating over dx. Okay, and then we can simplify a little bit. So just as a reminder, if you're integrating a delta function, it's going to give you 1 if your value of x hits the delta function, and it's going to pick out the value of x where the argument inside the delta function is equal to 0. And if you don't hit that value of x in your integral, then you'll just get 0. Okay. So anyway, since we're integrating over infinite values of x, we're going to hit each of these delta functions, and we're going to end up as a sum of e to the I q, and then pick out every value of x where this the argument of the delta function is 0. So that is u1a, and then we can just write this as a sum over u1 of cosine q u1a plus I sine q u1a. So we can make a simplification at this point. So we're only going to keep the cosine terms, and this is because the sine terms will end up averaging out to 0. So as a reminder, we are adding out over all of the integers u1, negative integers and positive integers. And sine is an odd function, so sine x is equal to negative sine minus x. So basically, when we have for instance, sine qa and sine minus qa, those are going to yield a negative of each other. So then they're going to add to 0. So we're going to drop the sine terms for that reason, and we are just left with the following. So R of Q is equal to sum over U1 cosine of Q U1A. Okay, so at this point, we are almost done. So we know that U1 is an integer. We know that A is the lattice constant. It's the spacing between all of our lattice points. And then we need to figure out, are there any constraints that exist on Q? So it turns out there are constraints that exist on Q. So if we had some arbitrary value of Q, this sum would tend to be 0 as the number of terms goes to infinity. However, if Q is a specific value, then this is not true. So this is going to be not equal to 0 as number of terms goes, whoops, that's not how you spell goes to infinity. So this equation is not going to be 0 as the number of terms goes to infinity if each of the cosines is equal to 1. So if Q is equal to some integer times 2 pi over A. So if you consider all the possible values of Q that make this Fourier transform not be equal to 0 in the limit of an infinitely large system, then what you end up with is that the permissible values of Q are basically as follows. So you have 0, it goes in both directions. You have 2 pi over A, 4 pi over A, etc. Then in the other direction, minus 2 pi over A, etc. And this is precisely the reciprocal lattice. It has the spacing of the points equal to 2 pi divided by the lattice constant of the direct lattice. So this same sort of argument can be repeated for a three-dimensional system. So here, basically, what is used is a statement from earlier in the lecture that, well, let me write it this one, that BI dotted with AI is going to be equal to 2 pi delta ij. All right, so anyway, so just to summarize, in one dimension, it was shown here that the Fourier transform of the direct lattice is the reciprocal lattice. This same argument can be performed in 3 dimensions as well. I won't go into that, but this is a general piece of intuition that you should keep in mind, that the reciprocal lattice represents the Fourier transform of the direct lattice. So that's one way of thinking about the reciprocal lattice. Another way that one might want to think of the reciprocal lattice in some contexts is in terms of specific plane wave states. Okay, so let's consider first a generic plane wave e to the I k dot r. Okay, so let me explain what this is. So first of all, plane wave, not plane like ordinary, but plane like a plane. And the idea of a plane wave is like the name sounds. You can pick some plane in space where the amplitude of this wave is going to be the same everywhere along the plane. Okay, so uh, so R is the spatial is sort of the real space dimension. So it in 3 dimensions. We write it as coordinate x, y, z, and then k is sort of the wave number of the plane wave that also encodes information about what direction the wave is traveling. And we will come back to this concept in a little bit, but just as a reminder, the amplitude of k is equal to 2 pi divided by lambda. So it's encoding information about the wavelength from the magnitude, and then the vector direction tells you the direction the wave is traveling. Okay, so now let's consider a set of points R that constitute the Bragg lattice. So R is going to be equal to U1A1 plus U2A2 plus U3A3. Okay, so R is some vector in real space that points to some lattice point. Okay, so if we have some general plane wave, it will not generally have the periodicity of our lattice because our lattice has certain allowed points on it, and a plane wave, before I give you any more information, can in principle have any wavelength, any directions. So now let's consider the set of all wave vectors k, which yield plane waves that have the periodicity of the lattice. Okay. All right. So it turns out that this set of plane waves is basically the reciprocal lattice. So the values of plane waves that satisfy this statement, they make the reciprocal lattice. So let's state this mathematically. So let's say we have e to the I k dotted with R plus R. Okay, so R, lowercase r is any coordinate in real space, and uppercase R is some direct lattice vector. So, so because the R vector is defined as a translation operation, which leaves the lattice invariant, then this has to be equal to e to the I k dot R. Okay, and then if we just divide out common factors, we get that e to the I capital K dot R is equal to 1. And this expression can only be true if k dotted with r is equal to some integer multiple n times 2 pi. And this is indeed the one attribute of the reciprocal lattice. So this equation describes this statement for one vector of the reciprocal lattice, but we can see that if k is equal, if we just write this out, so k is going to be something that has the periodicity of the lattice, and it's also this also means that it can be described with the reciprocal lattice vectors. So then let's write it as v1 v1 plus V2, B2, plus V3, B3. And then this is going to be dotted with this expression for the direct lattice. So U1A1 plus U2A2 plus U3A3. And if we work this all out, keeping this equation right here in mind, then we basically get 2 pi times V1U1, sorry, V1U1 plus 2 pi times V2U2 plus 2 pi times V3U3. So this expression right here is indeed equal to an integer times 2 pi, because each of the prefactors with the 2 pi's is just an integer times an integer. So everything here is only integers times 2 pi. So the product of a reciprocal lattice vector and a direct lattice vector is always going to be 2 pi times an integer, just like a plane wave that has the periodicity of the lattice dotted with the reciprocal lattice vector will also yield the same answer. So that's sort of another way of thinking about the reciprocal lattice. It sort of represents sort of some select plane waves. And this definition is going to come more in handy when we think about actually measuring the reciprocal lattice using some form of electromagnetic radiation or wave-like particles. And then with that, we can learn about the structure in real space if we want that information. Okay. So this is a little bit of information or intuition about the reciprocal lattice. And now I want to connect this to actually learning about structure. So I'm going to give a little bit of background, and then I'll get into some sort of experimental data we can look at. Okay, so okay. So I want to begin with how I began this lecture, and this is in terms of Bragg's law. So basically, Bragg's law, you connect that to a crystal lattice by dividing your crystal into planes. So these planes have a spacing d. And there are many ways, there are multiple ways to divide a given crystal into planes, and we'll a little bit later we'll come to the consequences of this. But anyway, the drawing that I have here is maybe a derivation that you've seen before, but basically you have two rays that are incident at the same angle, which is called theta. And the first ray is reflected up here, and the second ray is reflected from the second plane. So ray 1 travels, let's call this one 1, let's call this one 2. Whoops, this one is 2. So ray 1 travels some distance longer than ray 2. It travels distance 2d sine theta longer than ray 2. So for these two rays to constructively interfere, this path length difference must be an integer multiple of the wavelength of light. So this is the path difference. This needs to be equal to some integer times the wavelength for constructive interference. And this is just Bragg's law. And I want to connect at this point Bragg's law to the reciprocal lattice. And to do that, we're going to be starting with the image on the right. So we're going to use slightly different notation than before. So we're going to think of our incoming light as being plane waves, Plane, plane, not ordinary plane. And the incident beam is going to be described as the complex exponential e to the I k r, where this wave number, wave vector k, is encoding information both about wavelength and about distance or about direction that the beam is going. So then we're going to consider 2 points in the crystal. So the gray blob is the crystal, and 1 point is the origin, and then the other point is some volume element dV that is a distance r from the origin. So then the wave comes in, it's going to get diffracted both from the origin point and from this volume element labeled dV, and it's going to exit this material with wave number k prime, or wave vector k prime rather, and the outgoing beam is going to be e to the I k prime dot r. I realize that this picture doesn't have the prime on the K. The reason for this is that usually the way that the experiments, at least to learn about structure, are done, is that the magnitude of the the wavelength of the outgoing light is the same as the incoming light. But anyway, just for being formal, I'm going to write the outgoing beam as e to the I k prime r, where k prime is encoding the wavelength and the direction of the outgoing beam. All right. So, so at this point, we're going to do something very similar to what is done on the left-hand side in the Bragg equation. So I'm going to do that on the next slide. So the first step is going to be to find the phase difference between the incoming beams as they travel to O as compared to dV. And the path length. Okay, so let's. Okay, so step 1, we're going to calculate phase difference. And this is going to be equal to the path length difference divided by the wavelength. So this piece right here, it tells us how many wavelengths fit into the path length difference, and then times 2 pi, this is going to tell us the fraction of a full cycle that this is. Okay, so then putting this together, we get r sine phi divided by lambda, the wavelength, times 2 pi. And let me go back to the previous slide to give a little bit more information. Okay, so basically phi is right here, and it is the angle that you get. That's the difference between the vector r that connects the origin to this point labeled dV, and then you have the perpendicular to the lower wave part of the wave right here. And essentially, this is the path length difference. And you can see graphically that this is equal to r sine phi. Okay, so this is just answering the question, how much longer does a beam that comes in over here travel relative to a beam that comes in over here? Okay, so that is what we have here. And then we are going to remind ourselves that 2 pi divided by lambda is equal to k. This is the definition of a wave number. So thus, this phase difference is going to be equal to k dot r. Okay, so this is just answering, uh, um, this is just the connecting the path length difference to a difference in phase of the wave. Okay, so so this is our phase difference, and then step 2 is the phase difference of the diffracted wave. Okay, so for the diffracted beam, we're going to go through the exact same exercise, and basically the result is going to be that, um, um, all right, so then that result is going to be that minus k prime dotted with r is equal to the phase difference on the other side. So essentially this phase difference right here. Okay, so so the total angle, the total phase difference is uh, is going to be equal to, it's going to be equal to k minus k prime dotted with r, and um, and and uh, and so that means that the wave that's scattered from, so going back to this image here, basically the wave that is scattered from the origin versus this volume element dv, there is an addition, a phase factor. Uh, there's a phase factor there that is equal to e to the I k minus k prime dotted with r. Okay, and we're going to define this difference in k as delta k. And let me just draw graphically. So we have some vector k, we have some other vector k prime, and then we have some difference between them, delta k. Okay, so um, good. So all right. So now what we're going to do is we're going to account for the fact that we are not just scattering, sort of comparing 2 points. They're not just 2 points involved, but there is an entire array of scatterers. Okay, so the total phase factor of this array of scatterers is equal to a sum over j e to the I delta k dotted with r j, where essentially j is all of the sets of points on the direct lattice. Let me actually write that as a capital R. So rj, where r is equal to u1a1 plus u2a2 plus u3a3. Okay, and then the intensity of the scattered beam is just given as the amplitude of all of these phase terms added together. So like this, amplitude squared, and this is equal to a sum over I and j e to the I delta k dotted with uh, uh, vector ri minus rj. Okay, so each of these points right here, so these are basically differences between 2 points on the direct lattice. So these are going to be translation vectors of the lattice, and then let me write that down. So sum over ij e to the I delta k, and this can be written as some integer u1 prime times a1 plus some integer u2 prime times a2 plus some integer u3 prime times a3. Okay, so each of these exponential terms will be 1 if delta k is equal to g. Okay, and um, and g is a reciprocal lattice vector. So basically, when this statement holds, essentially you have constructive interference. So one piece of information that I haven't given yet is, or maybe I have, but I'll just remind you, is that these experiments are usually done in what is called elastic, meaning the wavelength or the frequency of the incoming light is the same as the wavelength or frequency of the outgoing light. So that means uh, that the magnitude of k and the magnitude of k prime is going to be the same. And it also means that k squared is equal to k prime squared. Okay, so let's use this to rewrite the equation. So we have g is equal to k prime minus k. And then we have k plus g, just moving k to the other side, k plus g. Sorry, these are all supposed to be vectors. K plus g squared is equal to k prime squared, which is equal to k squared. And then so basically the k prime squared thing is just straight squaring both sides, and then the k squared is because the k once k prime squared is equal to k squared. But anyway, let's work out this left-hand side. So this equals to k squared plus 2k dot g plus g squared is equal to k squared. And then we get 2k dot g is plus g squared is equal to 0. And um, this is sort of one compact way to state the condition where you have constructive interference in terms of reciprocal lattice. We can also write this expression as 2k dot g is equal to g squared as opposed to minus g squared. The reason that we can do this is because if g is a reciprocal lattice vector, then so is minus g. Okay, so Anyway, this is just a compact way to write down Bragg's law in terms of reciprocal lattice. And just as a reminder, K is encoding information about the beam. So typically, let me not say typically, but most commonly, one would use X-rays to learn about structure. So here, K would encode the wavelength and direction of X-rays, and then there would be sort of select reciprocal lattice vectors where this equation could hold. Okay, so at this point, I want to connect. I want to connect more directly this equation to Bragg's law. So I want to show that this is Bragg's law, but to do that, I'm going to have to make a little detour and talk about Miller indices. So Miller indices are basically ways of quantifying which planes of the crystal in real space that you're talking about. And the process for finding Miller indices is as following. So okay, the process of finding Miller indices is as follows. So step one is you find the intercepts on the axes in terms of lattice constants A1, A2, A3. Okay. And then you take the reciprocals of these numbers and reduce to the three smallest integers. And then you express these results as three numbers in parentheses. Okay, and I realize that these these three instructions don't mean much at this point. I'm going to have sort of a graphical representation in the next slide. That's going to be the representation for a cubic lattice. Okay. Oh, and uh, conventionally you don't use commas for this. You just write HKL, no commas. A lot of the time people put in commas there because it feels weird to do it without commas. But conventionally, no commas. Okay, so again, the Miller indices are basically like a way to express how you are slicing your crystal structure into planes. And let me make that more explicit here with an example of a cubic system. Oops. Okay, okay. So in these images, the Miller indices are given below each drawing. So, and then the plane shaded in gray is the plane that is being described. And these are all images in real space. So in real space, you can divide a crystal structure into planes in several different ways. So in this first example, the 001 plane corresponds to a plane that is perpendicular to the z-axis. And if we were to repeat this cube over and over, we would have, one plane and then another plane, a unit A below it, another unit A below it, and so on and so forth. So the Miller indices, each Miller index represents sort of an infinite series of parallel planes. The black triangle is just how they drew these drawings to represent the XZ plane. Just ignore the black triangle. Okay, so you can see that in a cubic system, there are sort of three equivalent planes that represent kind of the face of the cube and every equivalent. 1. So 0, 0, 1 is kind of the top of the cube. 1, 0, 0 is the side of the cube that intersects along the x-axis, and then 0, 1, 0 is intersecting along the y-axis. And again, let me sort of go through the 3 steps. Let me actually do that for, this row right here. Okay, so the first step is to find the intercepts. So let's say we wanted to slice up the crystal structure into these sort of diagonal planes that are drawn here in this drawing. So the first step is we would sort of draw the plane, and then we would try to figure out what is its Miller index. So let's do this one right here. So the first instruction is to find the intercepts on the axes in terms of the lattice constants A1, A2, and A3. And also, I didn't write it down, but it should be noted that integer or fractional intercepts are fine. Okay, so let's go along X. So according to this graph, this plane drawn in gray intercepts the x-axis at 1 unit or 1 lattice spacing along the x-axis. Okay, so that's the x-axis. Let's see what's happening on the y-axis. So on the y-axis, the plane is actually parallel to the y-axis. So it does not intercept the y-axis, so this would be infinity. And then finally on the z-axis, we can see that the intercept is at z equals 1 lattice unit, so that's 1. Okay, so then we take the reciprocal. So the reciprocal of 1 is 1, the reciprocal of infinity is 0, and then reciprocal of 1 is 1. Okay, and there's our 1, 0, 1. And then finally, the bottom row, I'm not going to go through the example here, but these are sort of representing planes that kind of cut through the diagonal on sort of the volume diagonal as opposed to the diagonal of one face. So anyway, these are just some examples of Miller indices. They don't just need to have ones in them. You can have 2, 1, 0, 3, 1, 0, so on and so forth. And we'll see we won't see examples, but we'll see notation that uses it. Okay, so these are what Miller indices are. And at this point, I want to do where I have space. I guess I'm going to have to insert a page. All right. So I'm going to do, okay. Alrighty, so I'm just going to do a very quick derivation. Am I going to do, sure, I'll do a derivation. Okay, so any crystal can be divided up into planes, and it turns out that the spacing between these planes for some given Miller index DHKL is equal to 2 pi divided by the magnitude of a reciprocal lattice vector, such that where G is equal to HB1 plus KB2 plus LB3, where H, K, and L are no longer arbitrary indices, but there are arbitrary integers, I should say, but they are the Miller indices that are associated with these specific planes of the crystal. Okay, so let's go ahead and do this. Oh, and I should mention that this G is actually normal to the plane of incidence or plane of interest. Okay. All right, so we're going to be, okay, so let's start with an equation that we had a little bit earlier. So 2K dotted with G is equal to G squared. Okay, so let's go ahead and do 2, and then the magnitude of k is going to be 2 pi divided by lambda times sine theta. I'll explain what that is in a little bit. And then we have our g, which is going to be equal to 2 pi divided by d h k l. And then simplifying this, we get 2 pi, or rather plugging it into g squared, we get 2 pi divided by d h, whoops, HKL squared is equal to what's on the left-hand side. Okay, so this is basically assuming that this statement is true, and then we'll show that we get Bragg's law from it. Okay, and let me just draw graphically. So this is 2 of the planes in question, and our beam is coming in with angle theta and outgoing with angle theta, and ditto on the next plane. So that's what theta is. Sorry, my drawing is not exactly parallel. Okay, so we can simplify the expression right here. We get 4 pi sine theta divided by lambda is equal to 2 pi divided by d HKL, where HKL is just labeling the specific d spacing. And finally, we can simplify even further to get 2 times d HKL times sine theta is equal to lambda. So this is just precisely the Bragg condition sans a factor of the integer n in front of lambda. And this factor of n is missing right here. Because in the definition of the Miller indices, we explicitly remove common integer divisors. So, for example, if we had h divided by n, k divided by n, l divided by n, we would just reduce this to HKL. Sorry about my commas. We would just reduce that to HKL when writing in terms of Miller indices. So basically here, I want to just close the loop in making the connection between Bragg's law and the reciprocal lattice. So, the piece of information that is needed to make that connection is that basically we can think of the periodic structure in a three-dimensional crystal as being a sort of equivalent planes, and there are multiple ways to slice up a given crystal structure into planes. Okay, so the last thing that I want to do is just do some very quick examples using salt. And these are just going to be visual examples so that you guys can see some data that is actually used in contemporary research. The examples that I'm going to be using are all going to be on rock salt, sodium chloride. So this is a cubic crystal structure. It's actually based on the FCC lattice. So the basis is 1 sodium and 1 chlorine atom. You can see that there is this basis attached to every point of the FCC lattice. There's only 1 unit cell shown. If it were, repeated, you would have the full picture. Okay. So just as a reminder, Bragg's law works if D is similar to lambda, and then in a crystal, D is going to be something like 1 to 10 angstrom. Okay, so you need to satisfy Bragg's law, you need to find something that has lambda comparable to D. So one choice is X-rays. So X-rays, they have, you could vary the wavelength of X-rays, but what's typically considered an X-ray has wavelength between 0.1 to 10 angstrom. So that works, that's the most common. Another example is neutrons. So this is something that I showed a little bit earlier. And with neutrons, we use the de Broglie wavelength. Lambda equals h divided by the momentum. H is Planck's constant. And this is also 0.3 to 2 angstrom, so neutrons work. And also you can get electrons to work. So electrons, same idea, you use a de Broglie wavelength and you can get roughly 0.121 angstrom for the de Broglie wavelength of electrons. So for the two examples that are sort of wave-like particles, the momentum of the particles is something that is controlled in order to achieve the desired de Broglie wavelength of the experiment. Okay, so the first method that I'm going to show, the first type of data is called Laue, and Laue is someone's name. An important thing to know about the Laue technique is that it uses white X-ray light. And white just means that there's multiple wavelengths in there. So it's not just monochromatic one color, it's many colors. And when you have many colors, many wavelengths, many values of K, you can access more reciprocal lattice points all at the same time. And Laue is not a technique to sort of learn what material do I have or what is the lattice spacing of this material. This is a technique if you have a single crystal to find its orientation. So essentially this technique, you get symmetry information from it. So in the example below, you can see that there are lots of dots, but you can also see that the image is sort of fourfold symmetric. So if you rotate it by 90 degrees, you get the same thing. And this is because the sodium chloride crystal is oriented with one of its fourfold symmetric axes. So it's a cubic material, so it has some fourfold symmetric axes, and one of them is oriented facing the beam. Okay, so that's Laue. A more common technique that's used is called XRD, where this stands for X-ray diffraction. And this is also sometimes called powder XRD, or for reasons that I'll explain in a little bit. Okay, so the idea with this experiment is that the different reciprocal lattice points are accessed by either rotating the sample if you have a single crystal, or if you have a powder or a polycrystal, then each of the little crystallites in there, since there's so many of them, they take on every possible orientation. So that is how, okay, so let me explain what these data show. So first of all, this is monochromatic, and copper K alpha is something like 1.5 kilo electron volts in energy. The x-axis here is actually 2 theta, where this theta is, if you recall from the Bragg's law, this is just this theta. And the reason that it's labeled 2 theta is because the total deflection of the beam is 2 theta relative to the planes of the material. So the idea that this experiment is essentially just, it can be read as Bragg's law. So let me just write down Bragg's law again. 2d sine theta is equal to n lambda. And typically you just set n equals to 1. Occasionally you'll see more than 1. Okay, so lambda is fixed and known. And then for D, if you have a given crystal, so if you're doing the experiment on one material that is a powder, so that it has every single orientation in the specimen, then there are sort of finite ways to slice up that crystal into parallel planes. And each of these peaks represents a different value of D. So a different value of DHKL. And indeed, above each of these peaks is which Miller index it corresponds to. And you can see for yourself that you're not just limited to things like 100, 111. You can have various integer combinations that describe how you can slice up your material into parallel planes. I just want to emphasize that for a given material, there's kind of finite ways to slice it up into planes and still meet the Bragg condition. And each of those finite ways corresponds to a given value of theta, given Bragg's formula, and that is what is plotted here. And the y-axis is just some arbitrary measure of intensity. All right, so the last experiment that I want to highlight is low energy electron diffraction. And this, there's not much to say here. It's sort of analogous to the neutron scattering data I've shown earlier. So basically, each of the bright spots represents a reciprocal lattice point. And it's a dead giveaway that this is an electron diffraction experiment because of this thing in the middle of the image that's sort of shadowing the part of the image. That thing is the electron gun. So, low energy electron diffraction, or LEED, tends to be a very surface sensitive technique. It only measures roughly 1 or 2 atomic layers. X-ray is a little bit more bulk sensitive, so it measures about a micron deep or so, depending on the energy of the X-rays. And finally, neutron scattering is a bulk sensitive technique. So although X-rays, neutrons, and electrons can sort of measure the same crystal structure, you might apply them in different contexts, and um, uh, and all of them can be viewed as essentially directly measuring the reciprocal lattice, which is a Fourier transform of the direct lattice. And then if you want information about the direct lattice, you have to sort of Fourier transform it back to get that information. All right, so that's it for this lecture.